Okay, class, let's have some fun here. I'm going to use a couple of data sets here that represent two bowlers, bowler A, bowler B. Okay? And I'm going to ask you this question. So suppose that you're in a bowling league and one of your players dropped out, so you're looking for a new person to join the league. And what I'm going to ask you is, which bowler would you like to have join your league? Okay, bowler A or bowler B? Let's take a look. These are the last 6 games that each of the bowlers bowled, and hopefully you'll choose based on the data. So, we're not going to talk about the individual. You want to pick the bowler that you think will do the best in the league. So which one would you pick? Well, one of the things that you might want to do initially here is say, well, I'd like to have the better bowler. Okay? So maybe one indicator of that is the bowler that has the better average of the two. So let's calculate the average for bowler A and average for bowler B. Okay? Add up all the scores, divide by n, we get our mean. Okay? Now, I will do that for us, and what we find is that both bowlers have exactly the same average. Okay? They both have the same mean in this case. And so that doesn't allow us to choose which bowler we're going to pick for our league. And in fact, brings us to, I hope, a good example of the importance, perhaps, of a measure of variability, a measure of spread outness. And that is, which of the bowlers is more variable. And so what we're going to do here is we're going to calculate the standard deviation for each of these bowlers. Okay? Now, by the way, you might think to yourself, and I hope you do, you might think to yourself, well, why don't we just use the range? Because this group has a much larger range than this group, and so that would give us a measure of variability as well. Well, we'll talk about the problem with range a little bit. Well, maybe I can talk about it now. The problem with a range is that you can have scores that are quite close together like these, and then have just one score that's really aberrant, that makes the range larger. And so you have to be careful. It's almost like the mode when we talk about measures of central tendency. The mode, I say, is a fickle measure of central tendency. In fact, I don't even like to call it a measure of central tendency, even though it's sort of in that group. But the mode can pop up just about anywhere. If you have a low frequency for all of your other scores, the mode can pop up far away from the central portion of the curve. So I'm very careful. And we have to think about the same thing with the range when we measure variability. We could go with straight up sum of squares. Since the two groups are equal size, I suppose we could compare variability by just looking at the sum of squares. The typical, sort of the gold standard, is to look at the standard deviation. This relates to our last video because this tells us, on average, how much do scores deviate from the mean here. So on average, how much do the scores deviate from 155? On average, how much do scores deviate from 155 here? And I mean, we could take a guess, right? So I look at 155, I'm looking at these scores. What would you say? On average, how much are they deviating? Maybe 5, right? maybe 8 points, something like that. Maybe 6.7 points. I don't know, something like that might be the standard deviation here. If we look over here, relative to a mean of 155, we see that scores are quite variable, and maybe my guess here, let's see, 155, I mean, I don't know, maybe my guess might be something like 15 or 18.7 or 21 or something in that range, you know, is my guess for standard deviation. Of course, we can do the calculations, okay? So remember our formula for standard deviation, it's sum of squares divided by n. We'll take the square root, okay? So we need to get the sum of squares first, and then it will be easy to just divide by 1, 2, 3, 4, 5, 6 and take the square root. I think what I would like you to do, when I say now, you can pause the video, and why don't we calculate the sum of squares here? Why don't we calculate the sum of squares? It's good practice for you, okay, using that formula. So, again, when I say now, you can pause the video, do the calculations. Let's see if your numbers match my numbers, okay? So, pause the video now. Okay, hopefully you're back and we have our values. And so this first item, what we're going to do is we're going to square each of these numbers. We're going to square each and add that together. And I think if you do that, you'll get 144,400. Okay. This next one, what we're going to do is we're going to take the total, that is, we're going to add up all of the x's, square that, and then we're going to divide by 6 in this case, okay? And so you should get this number, 144,150. Okay? If you didn't get those values, go back through it, see what you did wrong, drop me an email, whatever you need to do. So the sum of squares for bowler A ends up being 250. Okay, 250. Now I'm going to plug that in to this formula. By the way, in case I haven't said it, you'll certainly be able to look up the formulas for the exam. So we don't need to memorize these formulas, okay? I don't like memorization. I like thinking and figuring out. So here we go. 250 now divided by 6. Now make sure that you take the square root, because that's the big mistake, or one of the big mistakes, is that people they get caught up in the computations and they forget to take the square root. So we need to take the square root here. And 250 divided by 6, 41.67. Take the square root. So the square root is 6.45. And if you recall my guesses before we started this, I thought that the standard deviation was going to be around 5, 6, 7, 8, something like that. Because remember the concept, remember the meaning, okay? The standard deviation is the average amount that scores deviate from the mean. So we have a mean of 155 here. And we're saying that the average amount that scores deviate is 6.45 from that. Okay. By the way, that doesn't mean that every score deviates by that much. I mean, this score right here is right on the mean, right? So it deviates 0. This score is 10 points away from the mean. This score is 5 points away from the mean, so on and so forth. The average amount that scores deviate from the mean, 6.45. Now, we're going to do the same procedure here for our sum of squares and standard deviation. And for the second group, 148, 748 minus. And of course, since we have the same mean, that means that the addition of all these scores are the same. So it's 144, 150. Okay? Sum of squares then is 148, 748 minus 144, 150. So sum of squares here is 4598. Okay? 4598 divided by 6, take the square root. 4598 divided by 6, take the square root. And so for bowler B, the standard deviation is 27.68. And again, that's sort of is in agreement with our guesses for what we would see in that case. So the average is 155, and then on average, scores deviate from 155 by 27.63. And again, be careful when you describe this to someone, because not every score deviates by this much, right? This score is right on the mean. This score is 50 something away from the mean, 52 away from the mean, something like that. This is 25 away from the mean, and so on and so forth. So the average amount that scores deviate from the mean is 27.68. Okay? So hopefully you got those numbers. The computations aren't so bad. I hope with practice they get better. And so now I would ask you again, which bowler do you want to have on your team? Okay. Now, in this case, since the means are the same, I wouldn't say that one bowler is better than the other. They both have an average of 155. Okay. And I don't know what they've done before, right? Sometimes people get a little bit caught up in an eddy of like, well, what about what they did? This is all the information we have. Based on this information, who would you want on your bowling team? Now, there is no correct answer, but I want you to justify the answer that you give, okay? Now, some people say, I'd rather have bowler A. And typically, the rationale for that is that bowler A is not as variable, not as spread out, okay? And there's another way to say that, and I hope some of you, see this. We can say that bowler A is more consistent, okay? So if we talk about variability as a concept, right? We can talk about it as the inverse of consistency, okay? We can talk about it as the inverse of consistency. That is, if you're more consistent, you're less variable. Or if you're less variable, you're more consistent, right? So it's this inverse relationship. And in fact, bowler A is more consistent because bowler A is less variable. Okay? Bowler B, more variable, which means what? If you're more variable, you're far less consistent. Not much consistency here. Okay? So a lot of people would choose bowler A. I do kind of joke a little bit because I was on a bowling league when I taught in Pennsylvania for 10 years. I was in a bowling league, and my bowling scores looked much more like bowler B than bowler A. So I sometimes tease students. I said, "Oh, well, thanks very much. I'm not going to be on the league. You guys have chosen bowler A." That's okay. I would suggest, however, that you might want to pick bowler B. It's a much more exciting night because you never know what the hell's going to happen with bowler B. And in fact, that's also a concept related to consistency and variability. This is also a very important concept, and that is predictability. Okay? I'm much more able to predict, or I should say I have more confidence in predicting what bowler A is going to do. Bowler A is going to be around 155, pretty much a lot. Bowler B is all over the damn place, okay? And so it's hard for me to predict whether bowler B is going to bowl a 170 or a 120 or a 200, right? Which makes for a very exciting bowling night, by the way. The point here is, I don't care who you pick. I want you to understand what these numbers are providing for you. Variability, right? Overall average is the same. I created that to emphasize the importance here, or the utility of having this measure of variability, okay? If you want excitement and unpredictability, you go with bowler B. If you want consistent bowling and something that you're able to predict, then you go with something with less variability, right? More consistency. And by the way, this brings me to another point, and I really like to talk about variability because we all pay attention to variability. I mean, we have, a fancy name for it now. We're able to quantify it using standard deviation. But we all use the concept of variability to make decisions all the time, okay? So that sometimes you want to go to a restaurant that is predictable, right? It might not be the best food. The mean might be a little bit lower. But the service is always pretty good. The food is always pretty good. And every time I go, I can sort of rely on that. That is, it's predictable. It's consistent. Okay? Sometimes you might go to a restaurant where, the first time you went, the food was just awesome. That'd be equivalent to a high score, right? The food was just awesome. The service was great. I mean, it was just really good. And so you tell your friend, well, let's go there again. And then the next time you go, the food comes out 45 minutes late. It's cold. The waiter's rude. And it's like, what is up with this, right? Then you might go a third time, maybe. You might go a third time, and it's okay. And you go a fourth time, and it's awesome. And then a fifth time, and it's terrible. And so you're probably not going to go there too much more because everything is so inconsistent, it's hard to predict what you're going to see, okay? So, in terms of restaurants, it's the same thing. Now, consistency is okay, but consistency doesn't mean good quality. And I would argue that some fast food restaurants are really consistent. I mean, you go to one fast food restaurant and you get a cheeseburger in Syracuse, New York, and you go to the same chain and you get a cheeseburger in Athens, Georgia, and the same chain you get a cheeseburger in Portland, Oregon. And boy, those cheeseburgers are just about the same, indistinguishable. That is, consistency is really high because variability is really low. But we also have to pay attention to the quality of the food, okay? This tells you where you're at in a number line. This tells you how variable, okay? Sometimes people think consistency means quality, and I don't make that assessment. I like to have high quality, high consistency. I can deal with low quality, high consistency. That means it's predictable. The other options are what? Low quality inconsistency or high quality consistency, right? So there's two factors that play a role here, all right? And I mean, we can talk about friendships as well. We have friends that are very consistent sometimes in terms of their mood, in terms of their support. It's like, wow, very consistent, very consistent. Or we have people that, one day you talk to them and they're, really depressed, and the next day you talk to them and they're elated. The next day they're sort of average. That has to do with variability. So those people have much more variable moods than someone who's consistent, right? Or sometimes I talk about people, we all have friends that are always on time, right? Not much variability. You say we're going to meet at 10 o'clock, they show up at 9:58. You say we're going to meet at 10 o'clock, they show up at 10:01. You say we're going to meet at 10 o'clock, they show up at 10 o'clock, right? Then we have other friends where there's lots of variability, right? You say we're going to meet at 10 and they might show up at 10:15, or they might show up at 9:40, or they might show up at 10. This all has to do with variability and consistency. Variability and consistency, okay? And by the way, I have a friend who is always late by about 20 minutes, but he's very consistently late. And I know sometimes my other friend is like, where's so-and-so, I don't know where they are. I say, well, what time is it? Well, we're supposed to meet at 10 and it's 10:12. And I'm like, they'll be here at 10:20 because they're very consistent, but they're consistently late. Okay? So once again, this underscores the complexity of life, really. And what we're doing here is codifying it, and we're quantifying it so that we can talk about these variables. You know that this means the average amount that people differ from the mean. The average amount that people differ from the mean. I can then change the data set so the means are different and the standard deviations are different. What I'm doing here as a teacher is trying to tease out one variable at a time. When you do research or when you're working with someone in a clinical setting, you're going to have changes in the means and you're going to have changes in standard deviation. I mean, if this person had a mean of 165 and this person had a mean of 155 with the same standard deviations, then the decision about who we choose becomes a little bit more difficult because this person is a better bowler on average, 165, 155, but then we have to take into consideration how much do we value consistency, or how much do we not value variability, right? So those are the concepts. Those are the concepts, okay? I mean, we can talk about weather. The weather in the month of March tends to be much more variable than the weather in June, right? Sometimes it'll snow in March, sometimes it'll be 90 degrees in March, sometimes it'll, if we talk about June, there is some variability, but in general, it's going to be less variable than March. And we could talk about the same thing on the other end, like probably November is more variable than, let's say, August. Okay? All right, so I just wanted to bring together some real life stuff so that people understand that the math is describing the world. It's not separate from and different from the world. Okay? This is just helping us make some decisions. Okay, so let's talk about one more bowler. Okay, let's talk about bowler C. Okay, let's talk about bowler C. Maybe I should be putting names onto this. Of course, you now know that bowler B was Dr. Speck. But let's talk about bowler C, and let's look at some numbers for bowler C. These are the last 6 games that bowler C bowled. Let's take a look at bowler C's statistics. Okay. Well, lo and behold, when you do this, we find that bowler C actually has the same average as bowler A and B. Of course, I created these bowlers to have the same average, trying to emphasize here the role of variability in our assessment of each bowler and maybe in our decision making. Okay, so I'm going to let you once again calculate the sum of squares and calculate the standard deviation for bowler C, and I'm going to have you stop the video to do that. Stop the video now. Okay, so hopefully it went well, and hopefully you got a standard deviation of 36.02. Okay, what we're saying here is that the mean is 155. The average amount that scores deviate from the mean is 36.02. But this is a little bit problematic. I hope you see it. For bowler A and B, the scores kind of deviated symmetrically around the mean, right? Even though bowler B was much more variable, the mean was kind of in the center portion, right? Measure of central tendency. For both of A and B, but we just saw different spread outness, the variability, okay? Here we have something a little bit different, because if we talk about variability and we talk about consistency, I'm looking at bowler C and I'm like, you know, it says bowler C has an average of 155, and bowler C looks really variable. That is very inconsistent, very unpredictable in a way, right? But I'm looking at bowler C and I'm like, looking at these scores, I'm like, wow, I mean, that's actually a pretty consistent bowler, and it looks like they are bowling better than an average of 155. This is the average. This is the standard deviation. Nobody's lying to you. But I'm showing you this distribution because we have to be careful. Everybody remember what this kind of distribution is called? Yeah, it's a positively skewed. It's a positively skewed distribution. Okay? We have lots of numbers here and one, excuse me folks, it's a negatively skewed distribution. I'm not going to do the negatively, I'm not going to do the video over, okay? Negatively skewed distribution. I could say I made that mistake on purpose to make sure you're paying attention, but I just made the mistake. That's how it happens. I'm not going to get worked up over it. And here's what we're seeing. So a lot of numbers here, and then what? We have this one weird number here, 75. So this would be called a negatively skewed distribution. Now, in a previous video, we talked about the fact that the mean is not a good measure of central tendency in a positively skewed distribution. Well, the mean is also not a good measure of central tendency in a negatively skewed distribution as well. Because here's what the mean would look like down here at 155, and yet we have all these numbers up here, 169, 179, 170, 172, right? There's a whole bunch of blocks here for this bowler. We have one very low gain, and so what is that doing? It's pulling the mean away from this portion of the graph. It's pulling the mean this way, okay? Now, what would be the better measure of central tendency in a skewed distribution? This is review, right, for the exam. Well, a better measure of central tendency for a skewed distribution would be the median. And what would happen here if we use the median? And I'm not going to calculate it, but let's just see what would happen. We have 6 scores. We need to go up from the bottom. We need to go up the first 3. So 1, 2, 3, right? And then this would be the 4th. So the median would be, for this data set, the median would be something around 170. That's a little bit better description of what's going on for bowler C than a mean of 155. Okay, this is analogous to the example where we used the median for salaries rather than the mean, because the mean gets pulled out. Okay. And I mean, it's not a rule, right? What we're trying to do when we're doing descriptive statistics is to describe the data set. And so this is a better description of the data set than this for central tendency, okay? There's also an equivalent alternative for standard deviation, because this is a problematic bowler in a way to describe. What we're seeing is this bowler is pretty consistent, and not at 155, pretty consistent up around 170 with one aberrant score. Now, I'm going to talk a little bit about research in terms of the data telling us something. If I saw this bowler's data, and again, I've seen data like this when I'm in the lab collecting data with my research, the first thing I would do, I mean, I wonder if this is a mistake. 179, 169, 172, 165, 170. I wonder if that's supposed to be a 175, right? Well, let me double check. I'll go back and check the bowling scores. As it turns out, somehow we might be able to verify, nope, that's not a mistake. That was a really bad game, okay? I might talk to the bowler, and I'm saying, wow, your scores look pretty good, but that last game doesn't look like it fits. And maybe that bowler's going to say, oh, yeah, I think I broke my thumb in the 6th game, and I couldn't even hold on to the ball. Oh, okay. I'm telling you this from a research perspective because sometimes people make mistakes, right? My research assistant may have forgotten to put the 1 there, or put it so lightly and I couldn't see it. So we have to be aware of that, because that's a possibility, okay? Especially when you see data like this, it might be telling you something, and one of the somethings might be that it was a mistake, okay? If we find out that it's not a mistake, then we have to use it, okay? If we find out that this bowler said, I wrenched my thumb or I broke my finger and I couldn't hold the ball, well, then I'm not sure we should even include this when we're talking about this bowler's ability, okay? Those are options that you should investigate. I wouldn't assume either of those, but it's worth investigating because this just looks weird to me as a data set. Let's suppose that, nope, that's the real score. They both 75. And let's suppose that the person didn't injure themselves. So this is the real thing. I'm still uncomfortable reporting this as a descriptor. This is the largest standard deviation of all 3 bowlers. And yet I'm looking at this person and saying they're pretty consistent, but they had a really bad day or bad game, okay? So is there a better way that I could share these data in terms of describing? And the answer is yes. This is another example of a problem that statisticians come across, or researchers, and they solve the problem. It's a complex world. Have I mentioned that? Of course I have. It's a complex world, so maybe we want to describe this a little bit more. Well, so what we need to do in this case is, in a way, I want to talk about that kind of qualified descriptor for this person. They are pretty consistent except for this score, right? So what I'm going to do is I'm going to redraw this, hopefully make it a little simpler, right? We have a negatively skewed distribution. Let's do this. Okay. So there's one score down here that is really making this misleading, is what it ends up being. And this is another example. Please don't use the term "it throws the number off." Okay? That doesn't mean anything to me. What's happening here is this number is creating a huge sum of squares, and subsequently we have a large standard deviation. And it's misleading. It's not that it's false. Folks, this is the standard deviation. This is the standard deviation, okay? But I want to get into a little bit more complexity about describing the data set. So we have one number here, and we have a bunch of numbers here. And again, I'm making this sort of more generic. This is a small data set, so we can work with it. But this works for any negatively skewed distribution or positively skewed distribution, okay? What we're going to do here is we're going to divide this distribution into quarters. Now, we have actually done that, believe it or not, okay? We get the 25th percentile. What is the 25th percentile? The place where 25% of the scores fall at or below. We can look at the 50th percentile, also known as the median. We can look at the 75th percentile. That's the place where 75% of the scores fall at or below. And what have we done here? One quarter, second quarter, third quarter, fourth quarter. Okay? We've actually split this up into quarters. 25th percentile, otherwise known as Q1. 75th percentile, otherwise known as Q3. Okay? 50th percentile, otherwise known as the median otherwise known as Q2, okay? But we're going to look at Q3 minus Q1. That is, we're going to look at this interval, okay? What does that interval tell us? It tells us, now listen carefully. If you have questions, please email me. If we subtract Q1 from Q3, it tells us the range, the distance, tells us the distance, because this is going to be an x value that we get for Q1. This is going to be an x value we get for Q2. This is called the interquartile range. This is called the interquartile range. Q3 minus Q1 is called the interquartile range. That tells us where the middle 50%. This is the only time I have talked about middle, okay? It tells us the middle 50%. So in here, 50%, the middle 50% of the scores fall. Big deal, big deal. What does that do for us? Well, it allows us to disregard this extreme. Of course, it also allows us to disregard this extreme. So if it was a positively skewed distribution, we would use the same procedure as the negatively skewed distribution, okay? It tells us the middle 50%. It allows us to disregard extremes like this, okay? For this small data set, where would Q1 be? Well, we would need to go up 1.5 scores, right? So Q1 would be 1.5 scores, so something around 169. Okay, 165, 169, 168, something like that. That would be Q1. What would be Q3? Well, if we have 6 scores, we need to go through 75% of it. We'd go through, what, 4.5 scores? 1, 2, 3, 4.5. So around 172 or 173, right? What did I say before? Q1 is 168 or 169, something like that, okay? I'm not doing the actual calculations. Maybe 173, something like that. So the distance that the middle 50% cover is really small. 5 points in this case. It's not 36 points, right? Again, we could do a more detailed analysis. If you look back at your notes, you guys did the 75th percentile. You guys did the 25th percentile. That's what you would do. You would actually get those values and subtract it, okay? We're going to do, and what that does is it allows us to disregard the extremes. Now, as a consumer of statistics, you need to know that that's what happens if people are reporting this, okay? This takes into account the extremes, but what is it doing? It's really misleading us, okay? And finally, what we're going to do is, everybody good with this? Well, let me do this. We're going to take Q3, subtract Q1, and we're going to divide by 2. This is called the semi-interquartile range. Semi. We're dividing by 2, okay? Semi-interquartile range. Now, some people say, why do you divide by 2? Why do you divide by 2? Well, when I was first starting teaching this course 30 years ago, I'm like, yeah, I don't know why you divide by 2, because this makes sense to me, right? The middle 50%. Interquartile range tells you this is the range where the middle 50% of the scores are, right? But there's a reason why we divide by 2. There's 2 reasons, actually. I had to figure this out, look it up, do some reading. When we have a skewed distribution, its very nature is asymmetrical, right? And so this part of the interquartile range is a little bit different than this part, right, in terms of the distance. So we're going to get the average distance. If we divide this distance by and this distance, add them up, divide by 2, we get sort of the average distance. But more importantly, relative to the standard deviation, if we had a symmetrical curve like that, where standard deviation would be the gold standard for describing variability, standard deviation tells you this distance. You double it to find this distance. So if the interquartile range gives us this distance, I'm going to divide by 2 to make a measure that is analogous to what the standard deviation is. I'm not going to have you calculate this on the exam. I'm going to be upfront with you because I already know that you can do the 75th percentile. I already know that you can do the 25th percentile. All you need to do is subtract those numbers and divide by 2. I'm not concerned that you know how to calculate this, because I'm assuming you do. I will absolutely ask you, what's the point of using this? When you have a skewed distribution, this is misleading. Standard deviation. When you have a skewed distribution, this is misleading, the mean. So for a skewed distribution, we typically use the median and the semi-interquartile range. This tells us where the numbers are centered, that is, measure of central tendency. This tells us variability. Measure of central tendency, variability. Sort of a marriage. When we use the median, probably use semi-interquartile range. If we're able to use the mean, it is our gold standard, and it's the measure you should use when you have a symmetrical distribution. Mean and standard deviation are the sort of the gold standard pair. If you have a funky situation, then you use a more appropriate, a less misleading pair of descriptors. Okay, so that's basically chapter 1 through 4, and our next video will start with chapter 5.